To understand how the human brain makes decisions, behavioral scientists rely on the dual process model, dividing the brain into two competing modes of thought. On the left is System 1, generating fast emotional impulses. On the right is System 2, designed for slow, rational analysis. In adolescence, the emotional engines of System 1 overdrive, and the analytical logic of System 2 cannot apply the brakes. Researchers tested this assumption by putting adolescents through standard laboratory gambling tasks, expecting their immature System 2 to fail at basic probabilistic reasoning. The results contradicted the model. When tasked with calculating raw mathematical expected value, multiplying the probability of a win by the magnitude of the reward, adolescents frequently outperformed adults. They proved to be highly capable analytical calculators. If teenagers actively compute the math of a risk and choose to take it anyway, their behavior cannot be categorized as a lack of logic. The dual process model fails to explain a brain that is simultaneously highly analytical and highly vulnerable. To resolve this, researchers utilize fuzzy trace theory. This model divides memory and reasoning into two parallel tracks. The first is verbatim processing. This is the brain's mechanism for encoding literal, precise, quantitative data, such as exact percentages or numerical dollar amounts. The second track is gist processing. Instead of storing precise details, the brain extracts a qualitative summary, forming categorical intuitions like good versus bad or safe versus dangerous. Fuzzy trace theory posits that as humans mature, cognitive development progresses toward a heavy reliance on gist, not away from it. This directly inverts the old assumption. Intuitive, impression-based reasoning is not a primitive flaw to be suppressed. It is the most advanced cognitive state. The acute danger of adolescence stems from an over-reliance on high-resolution verbatim logic. Teenagers are perfectly capable of calculating the math of a risky scenario, but they lack the accumulated experience required to extract the intuitive gist that would otherwise protect them. This cognitive shift is mirrored by the physical development of the adolescent brain. As this visualization shows, the brain undergoes radical synaptic pruning. Gray matter density hits its maximum during early adolescence. Following this peak, the brain eliminates weak synaptic connections, significantly reducing its own volume. While gray matter decreases, the brain increases its production of white matter through a process called myelination. This myelin acts as biological insulation, wrapping around surviving pathways. This greatly accelerates communication between distal networks, linking integration centers directly with sensory nodes in the parietal regions. A childhood brain relies on a dense, localized physical architecture. The adult brain operates on a sparse, highly interconnected network. The resulting neural architecture prioritizes speed and global integration over sheer computational volume. By physically pruning away the capacity to track every dense verbatim detail, this less is more architecture forces the extraction of high-quality summaries. The biological structure of the mature brain inherently precipitates the shift toward intuitive just processing. To see how the developing brain evaluates risk, look at this expected value matrix, plotting probability on the x-axis against reward magnitude on the y-axis. The nucleus accumbens processes this magnitude, yet surprisingly, adolescents exhibit less activation here during risk anticipation. This muted response reverses entirely when the outcome is delivered. When a high-magnitude reward is received, the adolescent data line drastically spikes above the adult baseline, effectively warping the top half of the magnitude scale. This localized neurological hyperreactivity distorts the brain's internal math. The variable for reward magnitude becomes heavily weighted in the verbatim expected value calculation. Adolescents clearly perceive the probability of the risk on the x-axis. But because their reward centers react so intensely to the payout, the perceived magnitude mathematically overrides the danger. Adolescent risk-taking is not an error in calculation. It is a mathematically optimal choice computed by a biologically skewed reward parameter. We can observe how this verbatim logic contrasts with adult intuition by looking at the classic framing effect paradigm, a standard measure of human rationality. This test presents two scenarios with identical expected values. The top branch frames a guaranteed gain versus a gamble. The bottom frames a guaranteed loss versus a gamble. Both gambles contain a zero complement, the statistical possibility of walking away with nothing, highlighted here. A rational actor should be indifferent between the choices because the math is identical. Yet adults consistently fail this test of rationality. In the gain frame, they overwhelmingly select the guaranteed option simply to avoid the zero complement. This predictable behavior relies entirely on categorical gist processing. The mature brain ignores precise probabilities, extracting a crude summary. Securing some is inherently better than risking none. Neurologically, these frame-consistent choices are accompanied by increased activation in both the amygdala and the orbital medial prefrontal cortex. Adolescents perform entirely differently. While adults skew toward the sure option, adolescent preference unexpectedly shifts toward the gamble, a phenomenon termed reverse framing. Fixating on the highest numerical payout, the adolescent brain becomes blind to the adjacent zero option. This behavior is the direct result of relying on verbatim processing. The adolescent runs a strict quantitative trade-off between the risk and the highest possible reward. Predictable irrationality is actually an advanced survival trait. The mature brain relies on intuitive biases to reject mathematically acceptable risks carrying categorically catastrophic stakes. As this flowchart demonstrates, we can map cognitive maturation by placing gist and verbatim processing as parallel operational tracks in the brain. Top-down prefrontal inhibition, managed by the DLPFC and ACC, increases with age, placing it above the tracks. True cognitive control relies primarily on defaulting to gist processing. A direct pathway connects gist to cognitive control, bypassing the brute force inhibition track entirely, while a separate variable for reward sensitivity acts as a multiplier strictly on the verbatim track. However, utilizing brute force cognitive suppression to constantly battle emotional impulses is an incredibly inefficient control mechanism. Gist processing allows the brain to rapidly categorize a scenario as dangerous. This immediate qualitative assessment cues protective internal values, avoiding a full statistical analysis. By interpreting a risk intuitively, the mature brain neatly sidesteps the magnitude-heavy verbatim calculations that trap adolescents, rendering top-down suppression unnecessary. This cognitive model dictates exactly how we should design real-world adolescent interventions, particularly for behaviors like reckless driving or sexual risk-taking. When safety programs provide teenagers with precise statistical probabilities regarding the dangers of these activities, the effort backfires. Feeding an adolescent precise numbers strictly activates their verbatim processing loop. It forces them to rerun the expected value calculations, pitting the new risk probability against their biologically heightened sensitivity to the reward. Adolescents already possess the data. They know the risks. What they lack is the structural intuition required to weigh categorical stakes. Effective interventions must shift away from outlining mathematical trade-offs. They require establishing absolute qualitative boundaries that teach the brain to recognize a bad bet without doing the math. Achieving adult rationality requires unlearning how to precisely calculate the price of a risk and learning how to intuitively grasp its value.